All right, so in this video, we're going to do the expected value. So this is module 4.2 moments. This is going to be the first half of it. Let me share screen to the whiteboard. All right, so the expected value could also be described as the mean of whatever you're looking at. So it's the formula for this. So if you say the expected value, the notation that we're going to be using. So if I say the expected value, let's say X is a random variable. X could be anything. It could be people entering the store. It could be people looking at your website. It could be portfolio returns. It could be the time between people arriving on a car lot. It could be anything, any random variable. So we're going to say X is our random variable, and the expected value of our X, the expected value or the mean, assuming we know all expected or all possible outcomes, we know all the probabilities of it. Let's say X was, maybe if this was people entering a car lot, this would be one person coming in on the car lot multiplied by the probability of X1 plus maybe two people coming into the car lot on a given hour, multiply the probability of X2 plus all the way to Xn. Xn, so Xn times the probability of Xn. So the expected value of our random variable is going to be the probability weighted average. So X1 through Xn are our possible outcomes, and it's weighted by the probability of each of those respective X values. And this, again, it could also be described as the mean. So let's say mu X is the mean or the expected value of X. And it should also be written with summation notation. So you do big sigma. Let's sum up. We have our i's, I equal 1 to n, and we have xi times the probability of xi, and then you just add all those up. They all different ways to write the same thing. So with this, let's kind of apply it. Let's say you have dice. Let's say possible values of the dice. So a six-sided dice. A six-sided dice. Let's do for this. You could have a 1, you could have a 2, you could have a 3, you could have a 4, you could have a 5, you could have a 6. And each of these, the probability of any of these x's or any of these values is going to be equal to the probability of any xi is going to be equal to the same thing. It's going to be 1 over 6. So the expected value for this, the expected value of X, if it was throwing, the expected value of throwing a six-sided dice would be 1 times the probability of 1 over 6 plus 2 times the probability of 1 over 6 plus all the way to 6 times probability of 1 over 6. This is kind of a weird case. It's 3.5. So if you did this enough, on average, you'd probably have a 3 or a 5. You can't have a 3.5 because it's not even in the data set. Let's apply it to something a little bit more different, because this is a business class. It's a finance class, financial data analytics. So let's apply it to maybe let's do a realtor. Let's do a realtor, maybe a car salesperson, and you have people coming in per hour. So let's say possible values of X. Let's say say possible values of X. Let's say maybe no more than 4, just to keep it simple. Let's say you have 0 people. Probability of that is maybe 1 over 2. And these are events. Let's say random variables. All right. So let's say 1 over 4, and probability of one person coming in. Let's say 1 over 8. Let's say one person coming in would be 1 over 4. Let's say 2 people coming in would be another 1 over 4. We have, let's do 3 people coming in would be another 1 over 4. And let's say probability of 4 people coming in would be another 1 over 8. So first thing, let's actually check to make sure this makes sense. So remember back in one of the previous videos, in order to the sum of all mutually exclusive and exhaustive events has to be 1. So if we add all this up, 1/8 plus 1/8 is 1/4. We have 4 1/4. So it checks out. So we're good there. So now let's say what would be our expected value of X. I think this was people coming in a car lot. So let's say 0 times 1/8, which is the probability of X1, plus 1 times the probability of 1/4, plus 2 multiplied by 1/4, plus 3 times 1/4, plus 4 times 1/8. If you solve for this, when you solve for this, you will have you would have your expected value, the expected value of people coming in on the car lot per hour. So if this was the distribution for your random variable, and you could have 0 to 4 people coming in, these are the respective probabilities. If you add all this up, this would be the expected value of people coming in onto the car lot in a given hour. So this would be 1/4 plus 2/4 plus 3/4 plus 4/8. So this would be 6/4 plus 1/2, which could be written as, which would be equal to it would be 8/4 is equal to 2. So the expected value of X would be 2 people coming in per hour. Another useful case for this, for the expected value, would be for portfolio returns. So let's take another step further. Before we do apply it to a portfolio, let's do let's say we have a function for our portfolio returns. Let's say we have two. Let's say we have two portfolio, or let's say we have 2 assets in it. Weight 1. So we've weighted it. So we weight 1 times the return 1. So this is our first asset. This would be asset number 1 plus weight 2 times return 2, and this would be our asset number 2. We do so. This is a little bit different than the other ones. If we want the expected value, a few things we have to talk about first. If we have the expected value, let's say we have a constant. So let's say AX. This would be the same as A times X1 times the probability of X1. It's a probability weighted average plus all the way to A. A is just a constant. So XN times probability of XN. We can factor out the A. You factor out the A, and then you have all of that, which is just the expected value of X, which is the mean of X. So A is a constant. I'll write that over here. Where A is a constant. It could be any constant. It could be 2. It could be 0.5. It could be 1,000. Another important thing to know about and to review, and you should have seen this before in a Stat 211 or Econ 225, whatever it is you took. But we'll talk about it again here, as it is important. You don't have to do any proofs in this class, but this will be important when we do regression analysis, just so we can kind of understand why we're doing what we're doing. So with this would be the same as, so the expected value of X plus plus Y would just be the expected value of X plus the expected value of Y. So these are 2 important rules that we need to think about whenever we apply this to portfolio returns. So now if we say we want the expected value, we want to know the average portfolio return, the expected value of RP, this would be the expected value of our weight 1 times return of asset 1 plus weight of asset 2 times return of asset 2. So remember, back from here, say this is 2, let's say this right here is 1. From formula 2, we know that this would be the same as the expected value of weight 1 times return 1 plus the expected value of weight 2 times return 2. And this should be familiar to you back from Finance 310 investments. But we'll talk about it here again. So now back from formula 1. Remember, weight 1 is a constant. That's a constant. R1 is our random variable. This is our return of our asset 1. Weight 1, however, is a constant, so we can factor that out. So this would mean weight 1 times the expected value of R1. Remember, the expected value of R1 would just be the mean. So that would just be the mean of R1. I do R bar for that. Plus weight 2, we factor it out, and we get R2. So this is how it can be applied to asset management or investments. but it's all the same thing. So this is the formulas work no matter what the random variable is. But this is how you would apply it to portfolio management or to calculate portfolio return. So this was in this video we talked about expected value, which is the first half of the math portion of the PDF 4.2. And next video we'll do the second half, which is variance.